Welcome to the 10th lecture on for NPTEL course on computer system optimization for machine learning. Today we will give you a brief recap of the course and then we will discuss about DenseNet. Okay, and believe me, that's the last neural network we will be discussing on. I know you probably are bored so far. And then we will discuss more interesting topic, which is technique to reduce the floating point operations. Okay. So, in the last lecture, in the last class, we discussed about inception V1, where the main contribution or the main concept was to apply this one by one convolution before the large convolutional filters. This one by one convolution reduce the number of weights such that the entire DNNs can be trained on one GPU. This is a very important statement. Probably at later point of time when we will discuss about DNN training, then we will see what is the importance of GPU during DNN training. And then since they introduced this one by one convolution, the number of multiplications reduced from 854 million to 358 million, right. After that, we discussed about ResNet, which introduces residual connection or the skip connection. Now, in ResNet also they have multiple version. They use the concept of one by one filter for ResNet 2. So, they use this one by one filter to reduce the computation and size. So, you can see that between these two ResNet block, the only difference is this one by one convolution before and after that 3 by 3 convolution. Okay. And of course, if we use more convolutional layer, then that makes the network deeper. So, using this one by one convolution, ResNet 34 became ResNet 50. Now, we will talk about DenseNet, right. So far, I mean, this I am listing out some popular DNNs, but this is not an exhaustive list. If you just search online, if you search in Google Scholar, you will see there are many other popular DNNs. But these are the DNNs which mostly people talk about, or they eventually evolve to be one of the most important ones. So, we talked about AliNet, AlexNet. Overfit is one DNN which we did not talk, you can look into it. VGGNet, then GoogleNet, and then ResNet we talked about. So, this particular figure is showing the accuracy of the top 5 error for different network over the time. So, you can see that AlexNet has like 17% error, then it got reduced by overfit, then it got further reduced in VGGNet as well as GoogleNet. ResNet further reduced the error. Now, the most important thing is the human level accuracy is here. This is the human level error, around 5%, right. Now, I mean, for that, I think this ImageNet dataset people, whoever created the ImageNet dataset, they probably ran some survey and then got this number. Now, most importantly, ResNet actually performed better than human, and that changed the perception of these machine learning algorithms. Before that, I mean, people were just thinking machine learning algorithm is there, but they probably cannot do as good as human being. But the ResNet 50 or the ResNet is the first network which actually showed the real value of the machine learning algorithm by reducing the error of the ImageNet dataset or the classification error of the ImageNet dataset lower than the human error, which is a very big breakthrough. Now, this table is showing the summary of popular DNNs. I mean, there are many numbers, but since it is a systems course, computer systems course, I want to highlight few numbers. So, you can see the numbers are shown for AliNet 5, AlexNet, VG16, GoogleNet, ResNet 50, all the networks which we have discussed so far, right. Now, if we see the number of weights as well as the number of multiply and accumulate operation in the convolutional layer, you will see that there is a huge increase over the time from AliNet 5 to ResNet 50. So, you can see the number of weight is like 2.6 K from AliNet 5 to 23.5 million for ResNet 50, right. So, in VGG16 also there is like 14.7 million weight, which is again very high, right. Not only that, of course, if we have more number of weights, then our expectation is the number of multiply and accumulate operation is also higher, and that is the case happening here too. So, the number of multiply and accumulate operation for AliNet 5 is 283 K, but when we reached ResNet 50, the number of multiply and accumulate was 3.86 billion. Not only that, if you see VG16 has 15.3 billion of multiply and accumulate operation. So, one reason why ResNet 50 has less number of multiply and accumulate operation than VG16 is introduction of those one by one convolutions. So, if you remember, ResNet 50 has one by one convolution, GoogleNet has one by one convolution, and these one by one convolution is actually helping to reduce the number of multiply and accumulate. In VG16, the number of multiply and accumulate operation is much higher than GoogleNet or ResNet 50. But if you remember, let me go to the previous slide. If you see, the VG16 has higher error than GoogleNet or ResNet 50, right. So, that is one observation. Another observation is the fully connected layer also contribute a lot in terms of weights as well as the number of multiply and accumulate operation. So, in case of ResNet, you can see that 2 million weights are coming from fully connected layers, and then since fully connected layers are like if you remember in fully connected layers, the kernel size is exactly same as the input feature size. So, how many ever weights are there, we will have same number of multiply and accumulate operations. So, that is why the number of multiply and accumulate operation has is same as the number of weights for the fully connected layers, right. In total, you can see, I mean, for ResNet, the total number of multiply and number of weight is 25.5 million, and then the total number of multiply and accumulate operation is 3.9 billion. For VG16, it is 15.5 billion. You can imagine the scale of this network, right? It is a huge scale, correct. 15.5 billion operations are happening just to recognize some images or just to classify some images, right. And if we do not handle all these 15.5 billion operations, 15.5 billion multiply and accumulate operation, it will take too much time to infer just one image, right, to do inference of just one image. And not only that, I mean, inference is one operation, yes, but then think about training time will also be very high, right. So, that is why it is very important to study like how we can execute, how we can program these large machine learning algorithms, so that they like the training as well as the inference finish in reasonable amount of time. Okay. Now, with that, let us discuss about DenseNet. So, in DenseNet, as the name suggests, it is more denser. They introduce more skip connection not only from the previous layer, but from many past layers to strengthen the feature map propagation and feature reuse. Okay. So, that is the main motivation of DenseNet. Now, feature maps are concatenated, then rather added. So, in case of ResNet, if you remember that in the residual block x was coming, and then after the output of the x we are adding, right. So, that was the residual connection. So, this was the addition in case of ResNet, right, in case of ResNet. But then in DenseNet, this addition does not happen. Instead, we do concatenation. Okay. So, all these, whenever we have this dense connection, then some concatenation is happening here. Okay. Now, that only happens inside one dense block. So, you can see this is the input image, then some convolutional layer, then we have dense block 1, and then there are multiple dense blocks. So, inside each dense block, there are concatenation from all the previous layers to the next layer. Okay. So, again, why are there blocks? They have been broken into blocks to limit depth and thus size of the combined feature maps, right. Now, let us compare the validation error between DenseNet and ResNet. So, this particular figure is showing the top one error with respect to number of parameters, and this particular figure is showing the top one error with respect to number of floating point operations. Again, parameters, you can think the number of weights involved in the neural network, and then the floating point operations, you can think how many number of multiply and accumulate operations are going on in the deep neural network, right. Now, as you can see, of course, I mean, probably there is no two DenseNet as well as ResNet with same number of parameters or same MAC, but if you like look closely at the same number of parameters. So, let us say at like 3 into 10 to the power 7 number of parameter, DenseNet has lesser error than ResNet, correct, at around 2 into 10 to the 7 10 to the 7 number of parameter also, you can see that ResNet 34 has higher error than DenseNet 201, right. So that means DenseNet is more efficient in terms of accuracy as well as number of parameters, because at the same number of parameter DenseNet is providing better accuracy than ResNet just by introducing dense connection. Now when we talk about, or if we see in terms of number of floating point operation, then also we will see that at same number of floating point operation, let us say around this point, which is probably around 0.80 into 10 to the power 10 floating point operations, you can see that at the same point, at around same number of floating point operations, ResNet 50 has higher validation error than DenseNet 201, right. So that says, I mean, this proves that ResNet is actually good. Of course it is good, but then introducing denser connection and then deeper layer, more layers, DenseNet provides better accuracy with less number of parameters as well as flops, right. Now so far, yeah, we have seen many networks, like we have seen ELINet, which is good for handwritten digit recognition. Then we discussed about the ImageNet dataset, where there is a challenge, ILSVRC challenge, and then we saw that we saw different winners of those challenges, AlexNet, then VGG, then Inception, then ResNet, then DenseNet. Also in between we discussed the number of parameters and as well as the number of floating point operations of these networks, of these DNNs. And if you remember that the number of parameters as well as the number of floating point operations or number of multiply and accumulate operations are very high for all these deeper and denser neural network, right. So that means when we do the computation, we have to do some trick in computation so that the number of parameters, I mean, we cannot change the number of parameters, right. I mean, if a DNN is fixed, the number of parameters is fixed. The only thing we can change is how we are performing the computation, right. Now depending on that, depending on the fact how we are performing the computation, probably the number of multiply and accumulate operation will be lesser, or the number of memory access will be lesser, and so on and so forth. And that is where the system implications come into the picture. Probably the same DenseNet can be executed in two different ways, and in one case probably it will take 1 second to do one inference, and in another case maybe we have done so many optimization that it can take 10 millisecond to perform one inference, right. So now on we will see all these computation technique to reduce the latency, or mainly the latency, or improve the hardware performance, improve the computation or execution performance for different ML model. We will start with DNN and then eventually we will land up to the newer and exciting, more exciting machine learning models. So let us start with some simple technique to reduce flops. Again, when we say flops, it can mean floating point operations per second or just floating point operations. So usually if you have floating point FLOP small s, that means floating point operations per second, although here by mistake I put it capital S only, it will be small s. So let us see, let us take one simple convolution. Let us say we have this image and then we are convolving this image with a 3 by 3 kernel. These are the weight values 369, 4, 8, 12, 5, 10, 15, and then we are producing one output image, right. So in this convolutional, in this process there will be some number of multiply and accumulate operation, right. Now we want to reduce the number of flops. So one way to reduce the number of flop is to perform spatially separable convolution. So if you look closely here, this particular matrix can actually be written as the product of one column vector and then one row vector, right. So you can decompose this matrix as a product of one column vector as well and one row vector. So that is called, now if we perform one convolution with this just one row column vector, then we can obtain an intermediate image, and then we perform the convolution with the row vector and then we get the output image. The answer will be exactly the same, the output will be exactly the same. Now since we have perform this separable convolution, spatially separable convolution, the number of computations will be lesser. You can do this exercise on your own. I will not explain in detail, but the bottom line is, if we perform this spatially separable convolution, then the number of multiply and accumulate operation will be less, which is a big advantage in terms of computation. But then there are some drawbacks of this spatially separable convolution. First drawback is, there is no prior knowledge on the filters, right? They are being learned. Whenever there is learning involved, that means those filters are getting updated when we are performing the training, right? That means it is not always possible to define that matrix decomposition. If I go back to the previous slide, here we took the numbers in such a convenient way that it can be decomposed in these two, in one column vector and then one row vector, right? But not necessarily we can always decompose the matrices or the filters in one column vector in one row vector, because again those convolution and kernels are being learned, right? And during learning we cannot like ensure that they will be always decomposable, right? So those constants need to be imposed, but again nobody knows that how to impose such constant that during training we can have those decomposable matrices and then we can perform the training, right. So that is why spatially separable convolution is probably not always possible, although it has good benefit in terms of reducing the number of computation. Now there is another technique to reduce the number of floating point operation, that is called depthwise separable convolution. Now in depthwise separable convolution there are two steps. One is pointwise convolution and another is depthwise separable convolution. We will see what are those two steps. Now just to give a quick reminder, in regular convolution, if we have a 12 by 12 by 3 image and if it gets convolved with 5 by 5 by 3 image with stride length of 1, then we get a 8 by 8 by 1 image. How do we get this number 8? Remember, if we have the image height of h by w by c and kernel height of r by s by c, and then if we have stride length of s, then the output image size is h minus r plus s, right. So here we will have 12 minus 5 plus 1, which is nothing but 8. Okay. So that is how we are getting this 8 by 8 by 1 image, correct. Now if we have 256 such kernels, then we will have 256 channels in the output image, which we already saw, right. Now let us see what happens in depthwise separable convolution. So as I was saying, there are two steps in depthwise separable convolution. So first is depthwise convolution. We have the same input image 12 by 12 by 3 and then we have a filter 5 by 5 by 3. Now in depthwise convolution we do not add the values across the channel. We will convolve each of the channel with each of the filter and then we will just put in one plane. We will not add across the channel. So in regular convolution we just add across the channels, right. So we will have this 8 by 8 by 3 images, right. Now once we have this 8 by 8 by 3 images, then we will perform something called pointwise convolution. Now in pointwise convolution we have, again in the previous step we have this 8 by 8 by 3 image and that gets convolved with a 1 by 1 by 3 filter. Now this is nothing but that 1 by 1 filter which we are talking about, right. Now if we convolve this 8 by 8 by 3 image with 1 by 1 by 3 filter through a regular convolution, then we will get 8 by 8 by 1 image, and then if we have 256 of them, then we will get a final output of 8 by 8 by 256, right. Now here the one big difference between the spatially separable convolution which I just talked about and then this depthwise separable convolution is, here during training only you can define the filter sizes and then the weights will be adjusted accordingly, right. We are not tweaking with the numbers, rather we are tweaking with we are playing with the filter sizes. So whenever we are playing with the filter sizes, that can be handled during training, but then if we want to play with the numbers, if we do not put the constants during training, After training, there is no guarantee that we can have the same trick with the numbers, right. That is why spatially separable convolution, which we just talked about, is not good. Depth-wise separable convolution is more practical. Now, this is the technique, or this is the process of depth-wise separable convolution. Now, let us see what is the advantage. Now, to understand the advantage of depth-wise separable convolution, we need to know how many multiplications are happening in both regular convolution and then depth-wise separable convolution. So, let us say just an quick recap. In regular convolution, if we have 12 by 12 by 3 image convolved with 5 by 5 by 3 filter and then 256 of them, then we will get the output of 8 by 8 by 256, right. In depth-wise separable convolution, we have two steps. First, we are performing this depth-wise convolution, where we are convolving this 12 by 12 by 3 with one filter of 5 by 5 by 1 by 3. This one is the number of filter, and then we do not add across the channel, as I was saying, right. So, the output will be 8 by 8 by 3. Then this 8 by 8 by 3 output is passed through this 1 by 1 by 3 filter, 256 of them, to obtain this 8 by 8 by 256 output, right. So, that is the depth-wise separable convolution, right. Now, let us see how many total multiplications are there in regular convolution. So, in regular convolution, we have 256 kernels, 256 5 by 5 by 3 kernels, and that moves 8 by 8 times. So, whenever it gets projected or it gets convolved once, it generates one pixel. So, since one pixel in the output, or one point in the output, since the output size is 8 by 8, the filter is moving 8 by 8 times, correct, and then we have 256 of the filters. So, all of them will move 8 by 8 times, and then they will do some multiplication, correct. So, the total number of multiplication is 256 5 by 5 by 3, because all these weights are getting multiplied with some number in the input feature map, and then they are moving 8 by 8 times. So, this is the total number of multiplication, 1.2 million, right. Now, let us see what is the total number of multiplication in depth-wise separable convolution. So, as a reminder, depth-wise separable convolution has two steps. First step is depth-wise convolution, where this 12 by 12 by 3 is getting convolved with 5 by 5 by 1 3 to produce this 8 by 8 by 3, right. So, here the number of multiplication is, again, that 5 by 5 is the image, 5 by 5 is the convolution kernel, and then we have 3 channels. So, all the 3 channels of this 5 by 5 convolution kernel will be moving 8 by 8 times. So, total 4800 multiplication, right. And then in the next step, in the point wise convolution, we have the same input 8 by 8 by 3 here going there, and then that gets convolved with 1 by 1 by 3 by 256 to obtain 8 by 8 by 256 output, right. Now, whenever we are performing this 1 by 1 convolution, that is nothing but element wise multiplication and then adding across the channel, right. So, that means for each of the filter, we have 3 by 8 by 8 number of multiplications, right. Why 8 by 8? Because the output size or this input size is 8 by 8. We have 3 channels in the input, and all those 8 by 8 by 3 numbers in the input will get multiplied by the 8 by 8 by 3, will get multiplied by the weights 1 by 1 by 3, right. And then since we have 256 of the filters, the total number of multiplication will be multiplied by 256. So, this is the total number of multiplication for point-wise convolution. So, we have two numbers here, one is 49,152 for point-wise convolution, and then for the depth-wise convolution, means depth-wise convolution step, we have 4800 multiplication. So, the total number of multiplication is this plus this, correct, which is nothing but this 53,952. Now, compare these two numbers, 1 million and then 53,952. In both cases, the input is 256 5 by 5 by 3, output is 8 by 8 by 256, right. In both cases, the input and output size is exactly the same, right. The only difference is how we are getting the output from the input, correct. In regular convolution, yes, we are convolving for all the 256 filters, and the major difference between this depth-wise convolution and the regular convolution is, in regular convolution all the 256 filters will get convolved, or these 256 big filters will get convolved with the original image. Now, here the big whenever we have a big filter, we are convolving once and then we are using the pointwise convolution or the one by one convolution again and again to get the same image or the same size of image, right. So, that is the biggest advantage of depth-wise separable convolution, that it reduces the number of computations by so much. Again, if we initialize the layer sizes like intended sizes for depth-wise convolution, and then if we train, then our hope is the training quality will exactly be the same, means the error or the accuracy will be exactly the same between depth-wise convolution and regular convolution, but the biggest difference is this huge improvement in terms of number of computation, and that is why we need to learn all these techniques, all these tricks to know how can we perform the same computation, how can we execute the same ML model, but with less number of time, right. Now, again, as I am saying, the intuition in the depth-wise separable convolution is with the transforming the image only once and then using the smaller kernel, but in the regular convolution the image is transformed many times. So, that is the biggest intuition behind the reduction, the huge reduction in terms of number of computation or number of max or number of multiplication for depth-wise separable convolution. With that, thank you for listening. In the next class, we will see more computations or more optimization in computation for deep neural networks. Thank you.